Okay, good morning, everybody. Welcome back to Bennett's Chemistry 12 tutorials. We are currently on, I think we're on episode, what are we on? 23 now. We're in the middle of the titration unit, and I've been going through a couple of different types of calculations you can do with titration data. So the last one I want to do with you, before we get into the titration curves, which will be next class, will be determining the percent ionization of an acid or a base. The technique I'm going to show you can work for either one. And because you can do a percent ionization, you can determine whether or not the acid or the base, whatever you're investigating, can be categorized as either weak or strong. And so, again, I've got a scenario up here on the board that we're going to work with. Again, at this point, there are previous videos that were going into the mechanics and the theory behind all of the titration and how you might do it, things to pay attention to, how do you use the burette and things of that nature. So all of that stuff I'm skipping. I'm just kind of cutting to the chase, assuming you know all of that technique stuff. Okay, so here's a scenario. And the scenario asks you to prove something. Okay, and titration will be the experimental technique that you would use to prove what I'm about to ask. Okay, so up here on the board, in case you can't see it, in case it's a little blurry for you. So here's the scenario. An acidic solution of HX, okay, HX being the generic formula for a monoprotic acid. Notice it didn't say weak or strong. So solution of HX, monoprotic acid, has a pH of 1.82 at 25 degrees. 25 degrees is important there because at 25 degrees we know something about pH relative to 14 and all that kind of stuff. So it's typically in there. Might as well get used to that language. pH of 1.82. Titration of 10 ml samples. Okay, so samples plural. So obviously in the process, multiple trials were done of the solution using standardized, so of known concentration, 0.250 molar sodium hydroxide. Okay, required an average of 44.93 milliliters of that solution to reach the equivalence. Okay, so however many trials we did, 2, 3, 4, 5, whatever, when you took 10 ml samples of this unknown acid HX thing, the average pH of those samples was 1.82. The average volume of each sample was 10.0 milliliters, and the average amount of sodium hydroxide used to titrate each one was 44.93. Of course, if I had a data table up and I had 4 different trials, they wouldn't all be 44.93. You would have taken all 4 and you would have averaged them, and that's the value you would have gotten. Okay? Show by calculation, don't just make up something magical and write some little mythical statement saying this is what I believe. Show by calculation whether the acid HX is strong or weak. Okay, so that's kind of the scenario that's presented to you either in a laboratory situation or pen and paper, test, homework, whatever. Okay, so a couple of things, the theory that we have to go through before we actually tackle the titration. So the theory is you have to know the definition between strong and weak. Strong acids and or bases ionize or dissociate, if you want to say it that way. I like to say ionize. Ionize in water 100%. So whatever the acid concentration is, you will get that concentration of hydronium. Whatever the base concentration is, you will get that concentration of hydroxide. And so because the concentration of, and we'll stick to acid because we're talking about that, because if HX in the scenario was strong, whatever concentration of HX you had in the solution originally, that would have resulted in that exact same concentration of hydronium. The percent ionization, which is the concentration of hydronium produced divided by the concentration of the acid originally, that would have been 100% because they're the same number. And that would give you 1 times 100, that's 100%. If it's a weak acid, then whatever the acid concentration was, you will get less than 100%, and oftentimes quite a bit less, but certainly less than 100% of those molecules turning into hydronium. So let's say, I'll just throw out a number. Let's say the concentration of HX was 5 molar, and the concentration of the hydronium that you get from that was 0.006 molar. Well, clearly 5 molar producing only 0.006 molar is far less than 100% of the molecules. Therefore, the percent ionization would have been 0.006 divided by 5 times 100 to get percent. And that's how you would have gotten the percent ionization. It would have been far less than 100%. Okay, so our plan of attack here is, if you know the acid concentration originally, and then you know the hydronium concentration, you can do that division. Hydronium divided by the acid concentration, see what percent you get. If it's 100, plus or minus within like error, experimental error, then it's going to be strong. If it's less than 100%, and usually significantly, it's going to be termed weak. And so, like, if we end up getting a percentage of 98%, it's probably experimental error. It's probably meant to be 100%, and so therefore it would be a strong acid. If it's something far less than that, like we end up getting 10% or 8% or 0.3% or something of that nature, we'll classify it as weak. So that's kind of the big picture strategy of what we're going to do. So there's 2 pieces of information here, like in the actual scenario. Information, or point number 1, is the pH that's given. So pH of 1.82. That pH is telling you what the hydronium was of this acid in that acid solution, which tells me that the hydronium concentration in that solution is 10 to the power of the negative pH, which is 10 to the power of negative 1.82, which equals, and I pull out the calculator, my glasses, so I can actually see what I'm doing. So 10 to the power of negative 1.82. Make sure you put the negative in there. And so I get 0.015 sig figs molar. Okay, so that's kind of the critical number. So in your head, and I don't want you to kind of jump too far ahead, but in your head you should be saying, okay, so if I do the titration calculation part of this, and it comes out to 0.015 or something in that neighborhood, then the acid was strong, because the acid concentration then turned 100% into this hydronium concentration we just calculated. If the acid concentration is something bigger than that, say it's 1 molar, then 1 molar only produced 0.015 molar of hydronium, therefore it went less than 100% and therefore it's weak. So that's kind of what we're thinking before we even do the calculation. Now we do the titration calculation, right? So we go ahead and we do the titration calculation. So how do we do that? So number 1, all the data has kind of been given to you in a ready-to-go fashion. So it's already, you don't have to do any subtractions of initial and final burette readings, and you don't have to average the volumes and all that stuff. It's already been done for you. So what we start with now is we start with a neutralization equation. Okay, so what is the neutralization equation? Well, we've got that. It's a generic monoprotic acid. Monoprotic is actually key, because when we do the neutralization equation, whether it was monoprotic, diprotic, or triprotic, would change the stoichiometry here. So this is a monoprotic acid, and we titrated using sodium hydroxide. So we had a solution of HX, we titrated with NaOH, it went 100%, we formed the H of the acid and the OH from the base, formed water, and then we made the sodium salt of NaX. Okay, so we did that neutralization. Therefore, the moles of the acid and the moles of the base are going to be equal because this is a balanced chemical equation and it's a 1-to-1 ratio. Just a quick reminder, you know the formula of NaX is 1Na, 1X, because in this acid, if it's monoprotic, the charge on X must be -1. The charge on sodium is +1. Therefore, it's a 1-to-1 ratio, and that's the formula over there. It's kind of critical because you don't really see the balancing unless you get the formula of the salt correct. Okay, so now I know that the moles of the thing that I want to know, so the moles of HX are going to equal in a 1-to-1 ratio the moles of NaOH. So then I use my volume and my concentration of NaOH to actually calculate the moles of the NaOH. So this value over here is going to be 0.250 moles per liter. It's its concentration times the volume that was used. 4493. I converted it to liters so that it cancels, right? The liters cancel, so they cancel. And I end up with 0.25, oh, I can't see anything. 0.25 times 0.04493. And I get 3 sig figs, so I get 0.0112 moles. So the concentration, right? So moles is not what I want concentration. So the concentration of HX equals, now I'm going to put a little I down there because remember, titration always gives you the initial concentration of your acid. It takes you back in time to when you made that solution in the very first place. What was the number of moles of the acid that were added to the solution to make the original solution? So keep that one in mind. That's kind of a critical piece to remember. So the initial concentration of HX is going to be 0.0112 moles in that many liters. And that was right there, because it told me I was using an average of 10 milliliter samples of the acid. So that equals, move the decimal over 2 places, 1.12 molar. So the concentration of HX is 1.12 molar. Now, in your head, you should be taking this number right here and this number right here, and you should be comparing those two numbers, okay? So, and show by calculation, well, some people might just stop and say, okay, well, that's enough. I've kind of proven my point. There's the acid concentration, there's the hydronium, it's clearly less, so therefore it must have been an ionization less than 100%. You could also just take it a step further and say the percent ionization equals the hydronium over the acid concentration times 100, 0.015 divided by 1.12 times 100, which equals, where's clear? Oh, my goodness. Bad ears, fade to black. Oh my goodness, what's going on around here? I need a production assistant. Okay, so I've got 0.015 divided by 1.12 equals, move the decimal over 2 places, and I get 1.3%. Therefore, it's a weak acid. Okay, so the critical thing first stems from your understanding of the theory that weak and strong is defined by the percent that it ionizes. Then you move into, well, how do I get the hydronium and how do I get the initial acid concentration? titration will always give you initial acid concentration. That's the purpose of the technique. And so that's where the bottom of that ionization fraction is coming from. That's where this one down here, the 1.12, is coming from. The pH before you even do the titration, so in the question, that is giving you the hydronium that's up there. Now obviously if we were talking about a base and this was a basic solution and we gave you a pH of 12.10, you'd obviously have to change that. Well, maybe not obviously, but you'd have to change that to a pOH. So if we had 12.10, the pOH would be 1.90. That would give you the hydroxide. So with bases, you're talking about percent ionization being hydroxide concentration over the original base concentration, okay, rather than hydronium and acid. It's hydroxide and base. Figuring out the base concentration uses the exact same technique that you use to calculate the titration of an acid as well, right? So it's exactly the same that way. You just have to recognize you're talking hydroxide to base versus hydronium to acid, and then the whole principle remains the same. Okay, so this is actually a common technique. This is a common question. This is a common lab that is provided. I oftentimes even use it as a lab test to see if people understand the concept of ionization and can do a titration. Okay, so hopefully that helps. Next class, we're coming back and we're going to go into the concept of titration curves, which will be, you might have seen them before, but certainly how they arrive and some of the subtleties between them. How do you recognize what you're titrating? How do you recognize some characteristics of each thing that you're titrating? If you truly have an unknown, how do you figure out that you've got a monoprotic or diprotic? How do you figure out if you've got strong or weak just given the titration curve? Okay, so it gets a little bit more visual and then some identifying features of the curves. And that will be the last class of titration, will be that one. Okay, and then we'll be moving on to redox. So I'll see you later for titration curves, and that'll be our next one in the series. Okay, see you later. Take care.